to be here. Thanks, Tim, and thanks, Preslab, for inviting me. It's been great so far. One correction, the MA, Masters of Arts in Scotland is actually a bachelor's degree, so my bachelor's is in linguistics. And you're right that my master's was called something like cognitive science or whatnot, but it was really just natural language processing. Yeah. So today's talk is about retrieval augmentation as a shortcut to training data. And just to give you a bit of an outline of what you can expect, I will start with an intro to natural language generation and retrieval augmentation and how the latter applies to the former. I will then present in detail a recent work of mine on retrieval augmentation for image captioning. I will then discuss some further ideas I have for developing this line of research. I will briefly mention other research interests, especially with respect to what is being done here. And at the end, we'll have time for a Q&A, but if there are any pressing questions during the talk itself, feel free to interrupt me. So what is natural language generation? Well, it is the generation of text, one word at a time, usually conditioned on some sort of an input. In this example, the input that I have provided is a prompt, Abu Dhabi is best known for. And here we see that GPT-2, as used on the Hugging Face API, generates the continuation beaches, beaches, and beaches. It's all about the beaches, right? Text generation is used in a myriad of tasks. It's almost like a super task in itself because it's used for question answering, text summarization, machine translation, dialog generation, image captioning, and many, many more. Now, the other concept, the other family of tasks that we usually speak of in NLP is classification. And those are traditionally thought of as kind of orthogonal to text generation. But recent work has shown that text generation models can even perform classification. As we see in the example here, if our task is to perform sentiment analysis, GPT-2 can do that with just a few examples. And it took some cherry picking to get this to work, but you've all heard, I guess, of GPT-3, and GPT-3 is even better at doing that. So that is just to tell you how influential and important the task of text generation is. And now the other concept relevant to this talk is retrieval augmentation. Retrieval augmentation is not just used in text generation, it's a more general framework in which a model is conditioned not just on an input, but also on information retrieved from an external memory or what we might call a data store of information. And the idea basically is that by conditioning the model on this additional information, it should be better at predicting the desired output. This task is commonly used in this method of retrieval augmentation is commonly used in knowledge-intensive tasks, such as question answering, or another task that you might not be familiar with, Appositive Generation. This is a task that I worked on a couple of years ago, developing a data set for it. And what the task amounts to is the generation of a clarification for a named entity in a context in which this named entity might not be known. So in the example here, we have, in March 2017, Natalie Oresco was appointed as the board's executive director. If you're reading this a news article, for example, and you don't know anything about Ukrainian famous people, you might not know who this person is and what the significance of their new role is. But if you're told that this is the former Minister of Finance in Ukraine, this gives you some additional context to make sense of their role and helps you understand the general idea. And this clause, former Minister of Finance of Ukraine, is what is known as an appositive, and it is what we want to be able to generate in this task. So in this case, we would be doing retrieval from a knowledge base, such as Wikidata. Wikidata is a knowledge base that contains a lot of information about a lot of entities. When it comes to personal nouns, personal names, it would have information about date of birth, career, etc. So given this sort of bio block about Natalie Oresco, we can condition the model on the original input sentence and the new information, such that it can generate the correct context, the correct appositive for the named entity in this context. This use of retrieval augmentation is well known, it's well established, but it's actually another use of the method that I have been finding quite interesting in recent times. It is the use of retrieval augmentation as a shortcut to the training data. In this setup, the data store that we use for retrieval is actually populated with data samples for the task that we want to solve. So for input J, we might go to the data store and retrieve similar inputs, see what labels were assigned to those similar inputs, and use that information in order to predict an output for this input J. One example in which we can see this used in text generation is in dialog generation, where if we have an ongoing dialogue and we use this dialogue to find similar dialogues from the training data, we can see what the next turn was in this similar dialogue, and we can use that to condition the generation of the next agent turn. I've used this example, same as what I have in a recent paper on dialog generation, but since it's currently under review, that's all I'll say about it. If anybody's interested to talk about it more after the talk, please find me. Another example of retrieval augmentation as a shortcut to the training data comes in this work that we just finished last week on image captioning. It's titled Small Cap Lightweight Image Captioning Prompted with Retrieval Augmentation. And it's a work with a visiting PhD student we have at the Copenhagen lab, Bruno, called Brenda Ramos, her supervisor from Portugal, Bruno Martins, my colleague Desmond Elliott, and myself. And this paper, as of yesterday, is on arXiv, so if you're interested, you can find it there after the talk. What is image captioning? It's the task, pretty self-explanatory, the task of generating a description for the visual contents of an image. And the most obvious use for this task is to generate captions for the visually impaired so that they can, for example, interact with images that they see on social media and such. The recent trends in image captioning, similarly to every other NLP out there, is to scale up. Bigger models do better, models trained on more data for more time do better. And these are some of the state-of-the-art models we see here at the moment. The best one having somewhere in the range of 700 million parameters. And of course, with scaling up, problems start popping up with compute demands. Research in academia is not necessarily able to keep up with research that's being done at the big companies. It's not very green, and we should care about that, especially when we're in a hot place like this. So yeah, as a response to that, there is now the opposite trend too. Some recent works have tried to scale things back down and to see how close they can get to the performance of the large models with far less parameters. Notice that the x-axis here is now on a logarithmic scale because some of these models have as few as 14 million parameters, 28 or 43 million parameters, I think this one. And the metric we have here is CIDR, the most common metric used in image captioning. And this is evaluated on the COCO dataset, the most common dataset used in image captioning. So what we see here is that with far fewer parameters, we can actually still do really well on image captioning. So this is a promising direction for future work. And this is where small cap comes in. Small cap is a model that performs on par with other lightweight models while having only about, I think we said 17%, but let me put this in numbers. So the big version of small cap has 7 million parameters, medium has 3.6, and the smallest one has only 1.8 million parameters. And at this point, I should make a very important clarification. I'm talking about trainable parameters. So the full model actually has many more parameters. You'll find out why that is in a minute. But the training of the model itself operates with only a very small subset of parameters. And that is what makes all of these models lightweight for training. That is what reduces the compute demands for the training time. And small cap is basically equally good to other lightweight models while being much, much smaller than them. Now, let's see how it actually works. The general approach to image captioning is that of an encoder-decoder architecture, where an encoder takes in an input image, encodes it, passes it on to a decoder, and the decoder generates a caption for that image. And here is what small cap looks like. I know this is a lot to take in, so I'm giving you just a few seconds to look at it. And then let's look at a breakdown. So first we have the standard input stream, the one that we saw on the previous slide as well, where we have an input image. We're using a clip vision encoder. Clip is a transformer-based vision encoder, which actually takes in image patches and encodes each one into a fixed representation. This last hidden state of the clip encoder is then attended to by GPT-2, our language decoder, and GPT-2 then generates a caption for the model. The component over here, the encoder and the decoder, are both frozen. The only parameters of the model that are actually trained are in the cross-attention. And then we have input stream B. This is where the retrieval happens. That's the retrieval augmentation part. So what we're doing here is we're taking the input image, we're using it to query a data store of image captions. We're fetching a k number of nearest neighbors and using those as a sort of task demonstration. So these captions are conditioned on the input image. They are similar to the input image, and they're basically fitted into this prompt template. Similar images show. We have the list of similar captions, and then the final line of the prompt is this image shows, and this is where GPT-2 now generates a caption for the input image. And here is a little bit more detail about how the image to text retrieval actually works. So Clip, like I said, has a vision transformer component, and it also has a text encoder. And these two components are trained with a contrastive loss objective, which means that the two modalities, vision and text, are mapped into a shared vector space. That means that we can then query the representations obtained for different captions in the data store with the input image simply by computing the cosine similarity between these two and retrieving the nearest neighbors. And now we're back again at the full small cap approach, hopefully more clear now. This model is trained on Coco. Yes, we have the details here, the experimental setup. So the model is trained on Coco, and it is trained for less than 8 hours, which is nothing compared to what these huge models are trained on an NVIDIA 100 GPU. And since that's a large card, we also note that it's only trained for using 16 gigabytes of memory on that card, actually. We've set K to 4. That's a tuned hyperparameter of the model. We experiment with different dimensionality for the projection matrices inside of the cross-attention, because we not only want to have one component of the model trained while the others are frozen, but we can actually make this component smaller and smaller and smaller to a point where performance starts to degrade. But we want to find what is the limit, how far can we push? And the cross-attention is actually applied to every layer of GPT-2. As is standardly done. Here are the results on Coco. What we see is that down here we have small cap, the model with 7 million parameters, smaller cap 3.6, smallest cap 1.8. All of these models are, well, let's start from small cap. This model, yes, I have a little highlight here. It does not perform as well as Camel. We are okay with that, we acknowledge it. It has only 1/11 of the parameters of this lightweight model, and it's still very, very good. If you're not impressed right now, I'm okay with that, because in a minute you will be. And over here, we acknowledge the performance of the large models. Yes, they're far better, but they're also huge. They're not practical for deployment, at least for certain purposes. So their performance is there as a sort of ceiling where we would want to be one day with lightweight models. But this is where we actually are. And another interesting thing to notice is that with just 1.8 million trainable parameters, our model is still better than this model over here, for example, which has 14 million. Now, here is a little bit of an insight into whether retrieval is actually important. The simple answer is yes, it is. If we were to train the same architecture, frozen clip encoder, frozen clip decoder, trainable cross attention, without retrieval, this is where we are. So not only is our 7 million model more than 6 points behind on CIDR, but you can also see that performance degrades much faster in the smaller model versions when there is no retrieval. So this is a very interesting finding. We also see here that increasing the projection matrices, the dimensionality of the projection matrices to higher values where you then have 14 million trainable parameters or 28 million trainable parameters actually doesn't improve performance much. So 7 million is sort of the optimal model size, it seems. And retrieval is indeed very important for the performance of the model. Now we get to the really good part. Retrieval augmentation not only helps the model perform well with few trainable parameters, but it actually allows us to use data in a training-free fashion. So if at training time we have had the COCO data in the data store, at inference time we can swap it out for something else, or we can add data to it and evaluate the model performance with new data in a training-free fashion. The data sets that we consider for this part of the experiments are listed here. I've included COCO for reference. And then we also see a web data set with image captions that is quite sizable, and a bunch of human labeled data, which varies in size, and more interestingly, it varies in nature. Because we're doing image to text retrieval, we're not constrained to using image captioning data. We don't need an image to image for the comparison. We just need text that we consider would be relevant for generating image descriptions. So here we actually have a couple of image captioning data sets. Localized narratives is kind of an image captioning data set. It's a data set where people look at images with an eye tracker on and sort of narrate what they're looking at and what they're seeing. And then we have 2 video captioning data sets, 1 GIF captioning data set, and an audio data set, audio captioning data set. The references for all of them are at the end of the slides. And here we show the performance on no-caps. No-caps is a very important benchmark in image captioning because it evaluates the ability of a model to generalize to new visual concepts. No-caps actually has 3 subsets. The first one has in-domain concepts with respect to the COCO training data. The second one has similar but not quite the same concepts, that is the near domain. And then we also have a subset of entirely out of domain concepts, again, with respect to COCO. And here we see that small cap, our 7 million model, performs basically on par if we look at the entire is the average across the 3 subsets, performs on par with Camel. And if we then add more data to the data store of small cap, both web and human labeled from the previous slide, the model is actually extremely good at generalization. This is a very, very cool finding because, again, this is a model trained with few trainable parameters for a very short time. And the new data, this jump in performance, is achieved entirely without any additional training, fine-tuning, whatever. And a clarification, if you're familiar with the no-caps data set, they have the requirement that to participate in the challenge, you should not train on any additional image to text pairs. So that's important for 2 reasons. You're seeing that some of the large models from previous slides are not included here. That's because they actually didn't follow this requirement. Oscar is the only one that specifically took the effort to evaluate in a fair way. And again, a reminder, Oscar has 330 million parameters. We beat Oscar. We're very proud of that. But the other thing is that because we are doing image-to-text retrieval, we also fit in this requirement. If we were doing image-to-image retrieval, then one might argue that we are kind of using additional image-to-text pairs that the model learns from, but that is not the case here. All right, and so now that we've seen this generalization capability in small cap, we want to study it further. And what we do for this set of experiments is we focus on cross-domain transfer, where we take two of the image data sets previously mentioned, Flickr 30K and VizViz, and we actually place their own in-domain data in the data store to see how well the model does at exploiting that new data to adapt to the new domain. And here we see that in comparison to using Coco data in the data store, having Flickr or VizViz respectively data in the data store leads to kind of an okay improvement in Flickr, which to begin with is not that different than Coco, but actually to a very sizable improvement on VizViz. VizViz is a data set designed specifically for the visually impaired. Captions in VizViz are very detailed. They have certain characteristics that are not really common in Coco. So this is where we see that there was a bigger domain gap to begin with, and the model is doing a pretty good job at exploiting the new data in its data store in closing this gap. And here are some qualitative examples of what actually happens during this domain transfer. So if we're retrieving captions from Coco, where horses are very, very frequent, and camels, I think, are mentioned 22 times or something like that, the retrieved captions that we get are sort of reflecting that, and then the generated caption ends up mistaking the animal in the picture for a horse. When we go to in-domain data, we see many more matches for what the model should actually generate. We have 2 young girls, 2 children, and then camels are basically mentioned in every one of the retrieved captions. And consequently, the model generates a caption that correctly identifies the animal in the picture. In the other example, we see something similar, but even more extreme, more impressive, because there the Swanson brand is actually not mentioned at all in the Coco training data. But because it comes up in the retrieved captions from VizViz data, the model can generate this new concept, and it also predicts a more detailed caption for the picture in line with the nature of the VizViz data set. Now, something else we can do besides just swapping out the data set for new data is we can add more data to improve generalization. And indeed, what we see here is that with additional web data in the data store, performance, this is on validation data, by the way, performance in the data store, performance on Flickr 30K improves quite a bit. For VizViz, however, we don't see such an improvement. Again, we think that is because the distribution of that data set is so unique that it's not easily matched by other data. Interestingly, with human labeled data added to the in-domain data, we still see some improvement over in-domain, a little bit of a drop in performance for VizViz, but a little bit of an improvement for Flickr. But then really, like, neither this setting nor combining the two ends up giving us something overwhelmingly better than the web data. So our conclusion here is basically, if you have a very large amount of data that might be noisier than human labeled data, but it's big enough to be diverse, to represent different concepts, that is basically where you can get the most gain through this training free use of data in the data store. And here is a little bit of an insight what actually gets retrieved, because the results we see are telling us how the model generation performance benefits from what gets retrieved. But we have this clip vision encoder, clip text encoder, the retrieval basically depends on them. And here we see, when we have all of this data in the data store, what the clip representations end up giving us when we measure cosine similarity. So for no caps, we see an overwhelmingly high retrieval rate from web data. For Flickr 30K, we still see a very high rate. And then the next biggest chunk is Flickr in-domain data. And for BizWiz, again, kind of a unique data set, we see that the biggest chunk is actually in-domain data. But still, web data seems to be relevant to some extent. And one interesting observation to make is also all of these other data sets, even the video ones, the GIFs, even the, okay, maybe not so much the audio, I'm not gonna make claims that are not supported, but there is a considerable rate of retrieval for latex, for example, when we're considering Flickr images, which is interesting. It means that those captions do appear relevant to the input images that are in that data set. And here we see what the gains are from training a model, or sorry, no training for use of data, evaluating a model with each of these subsets of data in the data store. So we have in-domain data, and adding image captions or video captions or narratives or audio, each seem to help a little bit or more for the two data sets. But then again, we did find out that adding web data in general works better than human labeled data. So this is more of a, okay, it's interesting to see that video captions can help, audio captions can help. It still seems like just having a big chunk of data works better than that. So this might be relevant for people who work on data sets for which they specifically believe there might be benefits from these different types of data. But for our purposes, web data seems to work best. And this is what we see again here if we consider a kind of domain agnostic model, in which the main difference is we now have a data store down here that does not include in-domain data. So the simulated setup here is we're in a zero-shot setting. We don't have any in-domain data for the task that we're trying to solve. Let's see how well we can do with just other data sets. And again, here we see that web data is very useful, especially for Flickr, but even for BizWiz, it gives us a large improvement over. And at this point, you might be wondering, well, how do these results actually compare to state of the art for these data sets? And here is the answer. So we found that for both Flickr and BizWiz, the best setting, the best configuration in our experiments was to use in-domain data with web data in the data store. And if we compare the performance of our model to other models evaluated in a zero-shot setting, that is because we want to compare, we want to really showcase the benefit of being able to do training-free domain transfer. We see that small cap performs much better than the other two, but it still lags some way behind the state of the art. And this is where I think there is room for future work. Just noting again, these state of the art models are very large, pre-trained, fine-tuned, etc. So it very much depends on what your objectives are, but if you are in a setting where your training resources are constrained, your training time is constrained, then you can get pretty good results with our method. So the next steps I've been thinking about are, on the one hand, how can I continue this work? So I would like to work on methods for further improving the sort of in-context learning of the model, because what we have here with this retrieval is basically a form of in-context learning. The same example I showed earlier, I think I maybe have a slide on that. Yes. This example that we saw earlier, it showcases the in-context learning ability of GPT-2. This is an emergent ability in large pre-trained models. And it's one of the reasons they're becoming so popular these days. And it's just to give some context for what I mean by in-context learning, let's contrast it with in-weight learning. That is the standard machine learning setup where you have training data, you use it to compute a loss function, you try to optimize this function, you update the weights, that's in-weight training. In context learning, there's no gradients, there's no weight updates, and it's very appealing for that reason because it means you can apply a model without any training. And this is, like, it has some similarities to what we've done here. I think that there's lots of potential in taking these two things sort of closer together, where on the one hand, we still want to exploit emergent properties in large models, but on the other hand, we want to recognize that we can help that, we can push that further via this kind of retrieval-based training. And what I mentioned here is that I think there's especially potential in adversarial. Oh, wow, this slide is not. Okay, sorry. Yeah, adversarial training, meta learning, that sort of, that line of research. And then over here, a couple of more things. I think there's lots of potential in using this kind of method for making the model more general, where we're not necessarily just solving image captioning, but maybe also visual question answering. There's other tasks in the vision and language space that I think could be approached with this kind of general framework, and that is being done at the moment with these large pre-trained models. But I'm interested to see how far can we get with just retrieval-based kind of in-context learning, but inside, like, training, like bringing the in-context learning inside the training loop. How far can we get with this method? And then I think there's also still questions that are unanswered in terms of how does retrieval augmentation actually help? Is it really most helpful to just fetch the most similar items? Or is it something else that makes the model predictions better when we have retrieval? Is there other functions that we can use for retrieving items from our data store that would result in better performance? And that sort of brings us then to developing more elaborate methods for retrieval. So that was on the development side. On the application side, I actually have a task that is close to my heart because of recent interest I've had in the fate of refugees who find themselves in new countries, not speaking the language. Often there are no resources for them to learn the language of their host country. And I've been in touch with some NGOs in Turkey and Bulgaria about the language learning needs of the communities that they work with. And we've sort of come to an agreement that a very good framework for that as a sort of assistive to in-classroom learning is vision-based language learning. Why vision? Because vision-based language learning can actually be independent of the input of the first language, the native language of the learner, and instead we can have just images that are paired with text in the target language. For that purpose, however, we have to A, be able to generate good image captions, and B, be able to actually control the generation process. Because for different ages, we might want to present different vocabulary, different complexity of syntactic structures. Depending on the learning goals of the learner, we might want to adapt the vocabulary that we present to them. And lastly, the level of proficiency, of course, is going to play a role in that. And then just an array of other sort of, a mix of other research interests that are on my mind at the moment. With one of these NGOs in Turkey, we identified a very concrete problem that we want to work on, and I've spoken to a couple of you about it. I think there's going to be great potential for developing that here, because one of the problems that we will inevitably face in working on this task, to give a little bit more context, this is a situation where an interpreter is helping a refugee, often from an Arab background, communicate with a Turkish doctor or a Turkish lawyer, and the interpreter might not always know perfectly the dialect of the refugee, or they might actually not be well versed in the terminology of the health or legal domain. In that context, we want to have a device that is sort of monitoring the conversation and pings the participants every time when a mistranslation happens. To be able to do that, we have to be able to map from speech to text. We have to be able to find the correct translation, identify that the translation that has been offered by the interpreter is actually not optimal, and so on. So here, Arabic dialects are going to play a role, which is why for the moment, we've actually chosen to just kind of ignore that side of the problem and focus just on Turkish to Turkish post-editing. But it would be very cool to also take into consideration the issue of speech to text for Arabic. Then I'm just like very broadly interested in anything related to multilinguality, low resource NLP, and especially cross-cultural matters. That is, I think, maybe as a facial this year or a little bit earlier, becoming a very prominent topic in NLP. And I believe that it's extremely important both to acknowledge the different cultures of the people that we develop language technology for, but also to help them in bridging these cultural barriers. Then I have a general interest in probing language models, explaining their source of performance. Most recently, I've been working with the new pixel-based model. I don't know how familiar people are with this model. There was a little bit of a buzz on Twitter, but it's basically a language model that instead of taking in text input, renders the text as an image and then operates on the level of pixels. And this is extremely cool because it removes the vocabulary bottleneck and it allows for the processing of scripts that have not been seen at training time. And it actually performs pretty well. One problem that it currently has, and one of the works that I'm currently working on, is mapping back from images that the model reconstructs into text. Because right now, Pixel is a good encoder for downstream tasks, but it can't really be used for generation or even for masked language modeling because we're not able currently to map back from what the model generates as on the level of pixels into text. And I think that's my last slide. The next one is just references. Thank you guys so much. It's been a pleasure and I'm happy to answer your questions now.
Questions for our presenter?
I have a question. So it was not clear to me how, I mean, you have been talking about images, but you have been somehow learning from data sets that were about videos and about sound. And I'm a little bit confused how they relate to images and how we can.
Yeah, so the technical answer to that is the fact that we're doing image to text retrieval. So that's how it's possible technically. So the captions that we have in the data store here are just strings of text that we have taken from video captioning datasets, from audio captioning datasets. And the reason we expect that should work, and we actually see that it does help in this table over here. Oops. Yep. Is that when you're captioning videos, you also are referring to visual concepts. You're referring to there being a person in the image, the person doing something, or a car going down a road. So sometimes the captions can actually be very similar to how you would caption a fixed frame. With audio, it is a little bit trickier to see the connection, but actually there we still, if we look at the data, we still see people. So audio captioning is basically kind of speech recognition, but not quite. It amounts to still the captions that you see are things like that people are saying, and often they are discussing, their conversations are happening in a physical world, so they're still discussing concepts that they see around themselves or interact with, and that is why we see some benefit from using this data.
I guess the question in my mind was, do you have a shared embedding space for the image encoder and video encoder and audio encoder, or are you doing it, you decode and use the representation of whatever's ISB to retrieve just over the text? That was the bit I
So this is something that we have, I think like that's such a strong bias in people's minds that no matter how clear we try to make it, it doesn't come across. So let's see how I can try this again. So the thing is, in here, in this data store, we only have text. The videos don't matter. We didn't even download the videos. We just have a caption that says something like, a car is driving down a road and a person is crossing the street. And this is what we're encoding. We're not actually encoding the videos in any way. We're not encoding the audio. We're not doing anything with that part of the signal. That part of the data is just completely irrelevant to us.
So you're relying on the whatever DPR or BPR or whatever your retrieval method is to do the mapping from what happens to be here, image embeddings is your query to text, where the text is everything.
The text is everything.
So the retriever is learning that mapping from image embeddings to text embeddings.
The retriever is fixed. The retriever is not even a model. The retriever is literally just, we've encoded images with the clip vision encoder, we've encoded text with the text encoder, because these two components have been trained. Yeah, there's that whole like contrastive learning objective. So that these two modalities from the perspective of the space in which they're mapped are not even different.
Gotcha.
I actually still don't. So you have the image input, strong bias. I agree with you. Sorry. You have the input image, and then I mean these captions from 1 to n are coming from the same label data set of the input image.
They can be. So in some experiments where we say we use the COCO data in the data store, well, okay, I mean, it depends. Yeah, depends on the experiment. So let's say in the results that we show here, the captions come, yes, from the same data that the image comes from. And then of course, we've removed the 5 captions that actually correspond to that image, because that would be.
So my question is about, so you retrieve external text captions, right? That are similar. So so can you talk about the similarity function, like, you know, similar to what? Similar to both the image and the captions of the image, or?
No, just the image, So the input, okay, so if we have a data sample, a pair of image and text from COCO that, let's say we at validation time or inference time, we have input J, which is an image, and output J, which is, well, actually we have 5 reference captions for that image. We're using just the image to go to the retrieval data store. We retrieve captions that are similar to this image.
So how do you do that? Like you said, you don't have a model. So now you have the representation of the image.
Mm-hmm. So over here you have the representation of the image from the clip vision encoder, and the entire data store that consists of text is actually the representations of each item in it, of each sentence, is pre-computed with a clip text encoder. And the special thing about these two components, clip vision and clip text, is that they're trained with this contrastive loss objective, which means that they map inputs from the two modalities, image and text, into a shared space. So when you have an image that is mapped into the space of all of these and captions, you can just search for the nearest neighbors to that image, and these are the captions that you retrieve and that you then use for the retrieval augmentation.
Okay, so it's some sort of a model, really, like, you know.
Yeah. It's, I mean, this clip thing is pre-trained. It's something that we use off the shelf. What I was saying here is that we don't train. Yeah, maybe I should have phrased it like this. These two things again have the little ice cubes there because we don't train them, and also because to me, the fact that you're just computing cosine similarity is sort of model free in a sense, but you're completely right that you still need these clip components in order to put your inputs, your images and captions into this shared space.
Okay, so how do you, so I assume that, and then this will be my last point here. So I assume that you have the similarity function, which is coming from this previously trained model. And I assume that you put like a certain threshold as to how many of these external captions you will include.
We just use the fixed number of k equal to 4. That is something we tune at development time. We tried 1 through 6 captions, and we found that k equal to 4 works best.
So do you see any affinity between this approach, generally speaking, and weakly supervised learning, for example, with web data? So it seems like.
Yeah. So we had a lot of debates about whether we can call our model zero shot when we're evaluating on Flickr and we have Flickr data in the data store, for example, because we are giving the model access to data that is in domain. So it's not quite zero shot, but we're not updating the model weights on this data. So that is why I really think of it as most akin to in-context learning. So as much as in-context learning falls under the weak supervision framework, then yeah, I would agree that there's a similarity there.
I have a question. The CLIP model, what was it trained on? Which data sets?
I believe it's trained on a ton of data scraped from primarily Instagram, if I'm not mistaken, which is why for me it's almost strange that it's so good at encoding images in text, because this Instagram text rarely seems like natural text to me, but it's very, very good.
Okay, so it doesn't include the data that from the domains.
It's trained on scraped data. Well, okay, and then again, you always have the question of when you scrape data from the web, have you accidentally come across the data that is in your test set? But yeah, that is, I think it is mostly, if not only Instagram, so hopefully none of the relevant data is there.
Quick follow-up question.
Can I jump in first?
So you mentioned web data, use of web data. I mean, are these part of what is already encoded through CLIP, or do you actually go online and fetch additional data? And
we use a data set that was made available by one of the publications that I have cited at the end of the paper. It's actually the people who create the Blip model also create this web data set. And actually one clarification about that data set, it's not just raw web data. What they do is they get the raw web data, they train an image captioning model on it, and then they apply the image captioning model to the web images again. So it's actually synthetic data that is kind of cleaner than the raw data itself. They find that it works better. Improve on that, and the numbers I have are only measured on CPU, so I actually have no idea how that would change on GPU, but I can tell you that this sentence is generated by a retrieval tree model. Like if we don't have the retrieval component at all, if we just go image, clip, cross attention, GPT-2 prediction, the prediction time on this machine is 1.24 seconds. If you then pretend that you've pre-computed the retrieval and you just add this prompt here, because the prompt itself also takes time, like GPT-2 has to encode all of these tokens before it can start generating the next token, that basically doubles the prediction time. And then if we have to actually go and do the retrieval from the web data store, which is quite huge, that ends up giving us 4 times the double time. So it is definitely much slower. Again, caveat that I need to actually get these numbers on GPU. And the other thing is that I haven't mentioned here, but so when we pre-compute the data store, we use FICE, the Facebook efficient similarity search system to compute an index for this data store, and then we actually are able to do fairly fast nearest neighbor search in that way. But there are a lot of tricks in there that you can do to further improve the speed of the similarity search. So that's something that we'll be working on in the next month before the deadline.
And part of your model, the past for the other models, how does that scale as you scale up the size of the trainable component of your model? So it's partly a question of, for your model, if you increase the number of parameters by an order of magnitude, what's the influence on that inference time? But also, for a model which is 1 billion parameters instead of 10 million training parameters, say, obviously that's without the retrieval component, that's going to have an impact on inference time there, sort of offsetting the extra cost for you in terms of retrieval. So, I mean, it's a fiddly engineering analysis to be done, but is that sort of a direction you're looking at?
We have not considered that, but that's a really good point, that if we take one of these models with 600 million parameters and measure the inference time, it's going to be substantially different than what we get with just GPT-2. So we should definitely do that. But to answer the first part of your question about how performance, well, I guess you asked about how inference time changes with growing the parameters. We haven't really looked into that, because what we see here is that performance hardly changes as we go from 7 million to 14 million to 28, which was actually a kind of surprising finding, because of scaling up here. You always expect that throwing more parameters at your model is going to result in better performance, and that's not really what we see here. So it seems like there's a sort of bottleneck on the training only the cross attention is kind of a learning bottleneck. But it is a principal choice we've made to freeze the other two components, the encoder and decoder. So there's just no point in over parameterizing the model. That will slow down inference time, but it won't really improve performance much.
But do you think that the fact that you kept only one cross attention layer within each of the cross attention head in each of the layers?
Sorry, it's not one cross attention head. It's 12 cross attention heads. So it is multi-head attention, but it is, I was just trying to say, we're doing what you expect we're doing, but maybe I phrased it in a way, or maybe the fact that I said it made you think that I'm trying to say something that's not what you expected. But we, in terms of what the architecture of the cross attention is it's literally the default Hugging Face. What happens when you have an encoder and decoder and you just say, I want cross attention between these two. The only component we've played with is the projection, the size of the dimensionality of the projection matrices inside of the cross attention.
Questions?
So it's attractive that you are already training the parameters of the cross attention. You don't really fine tune the whole thing. But do you have a feeling how much you can be losing because of that? Do you think that if you had the appetite for that, and if you had the computational resources into that, do you have an estimate how much you can possibly losing? That's one question. And another question is, do you think that by the fact that you are doing only cross attention tuning, this actually helps you to do well out of domain? And if you actually kind of start fine-tuning the whole thing, then you kind of might really start overfitting to a specific domain.
Yeah, so you basically answered your first question with your second question. So yeah, I cannot give a real estimate. I can only say that CLIP is really, really good, and I don't expect that we would really get much more out of fine-tuning it. It's been trained on a lot of data for a lot of time. And yes, the only thing that could possibly happen if we were to fine-tune it further on the COCO data that we use for training is it would overfit that data. And even more so for GPT-2, I think, because the COCO captions are, they have such a distinct style. They're kind of general. It's always two women sitting on a couch, a woman standing in a kitchen. So this style, as soon as we start fine-tuning GPT-2 on this captioning style, I expect we'll lose a lot on the domain transfer that we see for BizWiz, for example. But we will get better performance for Coco, so there's always a trade-off.
Right at 12:30, so let's finish up with that perfectly timed ending and thank our speaker again.
So,